Hello class, and thank you for watching. In lesson 2.3, polynomial functions and end behavior, you will learn in this lesson how to graph a power function, how to use the leading coefficient to determine the end behaviors of a polynomial function, not just any function, but a polynomial function, and also determine the coefficient and power of a polynomial from a graph. So let's begin by first going over what a power function is. A power function is essentially just a function, again, and written in this format. F of x is equal to a times x raised to a power, hence the name power function. Now, the power functions, again, can have an exponent that is positive or negative, but today we're going to focus on the power functions that have a positive exponent, okay? And a power function is just essentially a type of monomial function where we have this coefficient of a multiplied with x to the power of n. What I want to do first is investigate, okay, what happens when I start changing this exponent on n and change it specifically from an even number to an odd number. So like example right here. Here we have the power function, as you see right up in the very top, you can't tell, but it's 1 times x to the power of 2. Our exponent is 2. If I change this exponent from a 2 to an odd number, let's say a 3, and then that's to, okay, that's weird. Why is it doing that? There, let me take that off. I don't want to do that. Let's delete that. Let's go back. There we go. If I change that exponent, sorry about that. If I change that exponent from a 2 to a 3, look how the graph changes. Now pay attention to this. Look what happens when I change it from an exponent of 3. Notice again at the very bottom, you see the 1x to the third power at the bottom of the screen. I change that from a 3 to a 4. Notice the shape again went back to a u, to almost like a parabola. Not a perfect parabola, but it looks exactly like x to the second power almost. Now if I change that exponent from a 4 to a 5, back from a 5 to 6, 6 to 7, to 8, to 9, and 10, and so on, you'll see that the graph of this power function is essentially becoming one of two possibilities. It becomes a U, or a U-shaped graph, and both ends are pointing upwards whenever our exponent is an even number, and it creates this curve again, this looking curve right there, where the left end is pointing downwards and the right end is pointing upwards, an increasing again function when n is an odd exponent. Even exponent, odd exponent. Even exponent, odd exponent. So you see the behavior of our function again behaves in one of two ways. It creates again this U-shaped thing, and the bigger the exponent, the flatter the U looks again at the base. Or it creates again a modified version of this cubic function, where again the higher the exponent, the flatter the cubic function kind of looks again around the origin, around the center, the origin of this thing. Now, if I change the exponent again, the coefficient from a positive 1 to a negative 1, multiply it again by a negative, then that's simply going to reflect our power function and have our power function be upside down. So our u's, our even functions, is facing downwards, and our odd powers is decreasing again this cubic function, and decreasing again from left to right. So notice again that this function is decreasing, this function is decreasing, and so on. So our functions decrease from left to right. So our power functions behave in one of those two possibilities. So let's again generalize this, and let's write this again in our notes. So for any power function, f of x equals to a times x to the power of n, if this value of n is an even number and we're multiplying this power function with a positive coefficient, then our power function is going to behave again like a parabola, where the left end of the parabola, or this function, is going to be pointing upwards, which we are going to describe using arrow notation as saying this. So the left end again is increasing without bound. So using arrow notation, we say that as x decreases, the function values increase without bound. And on the right side, since it's also pointing upwards, we say that as x increases to infinity without bound, as x approaches infinity, the function value approaches infinity as well. So this is how we're going to describe again the end behaviors of this power function. Now, if the power function has an even power but a negative coefficient, so in other words, so again, if this exponent is even, and now we have a negative number that we're multiplying our power with, then our power function is going to behave very similar to this function here that I'm going to graph. Regardless of what negative a value is, and regardless of what even exponent that is, it's going to behave very similar to this, where the left end and the right end are both going to be pointing downwards. So on the left, using arrow notation, we describe this by writing that x approaches negative infinity and f of x approaches negative infinity. To describe the right end, using arrow notation, we'll say that x approaches positive infinity, the function approaches negative infinity. So that's how we're describing again the left and right end of this function. Now, if we have an odd power, again like we saw, then those functions are going to again behave the same way. So let's write again f of x is equal to a positive coefficient x, and we're going to raise it to an odd number this time. Well, those functions are going to behave again like the cubic function, where we're going to increase from left to right and have it be symmetrical again to the origin. So as x approaches negative infinity, the function values also approach negative infinity, because again, this is what the left end is pointing. It's pointing downwards. Now to describe the right end, this end right there, using arrow notation, we write that x approaches positive infinity, the function values approach positive infinity. And finally, if I flip it around and have an odd power but a negative coefficient, then our power function simply gets flipped upside down, and instead of increasing, the function decreases. So this is a decreasing power function with an odd exponent. And the way we describe the left end is by now simply switching what we wrote on the previous slide. So as x approaches negative infinity, this time the function approaches positive infinity. And to describe the right end using arrow notation, we change f of x to approach negative infinity because it's decreasing without bound. So the way we're going to use this right here is we're going to use this characteristics of how these power functions behave and apply them to polynomials. Now, a polynomial function is written in this format here, where f of x is equal to a sub n times x to the power of n. Notice again, this looks essentially like a power function, plus a sub n minus 1 times x to the power of n minus 1, plus what looks like another power function and a bunch of other power functions again added together. So it's a bunch of monomials simply added together. Now, what makes it a polynomial is that these exponents here have to be positive numbers. So let's write this down. These values of n have to be positive numbers that are going to be greater than or equal to 1. And they have to be, again, integers or whole numbers, all right? Whole numbers, specifically whole numbers. They cannot be decimals, fractions. They definitely cannot be negative. but they have to be whole numbers that are going to be greater than or equal to 1. That's what makes these functions a polynomial, that these power functions have to have positive exponents. Now, the way that a function, the graph of these power functions is that they're going to be smooth curves that have no breaks or gaps and are continuous for all real numbers. And the domain of these polynomials is always the set of all real numbers. So from negative infinity to positive infinity. Now, because a polynomial, again, is a bunch of power functions being added together, the degree of the polynomial is going to be the largest exponent. We refer to this again as the degree. That's how we classify a polynomial, by looking at the largest exponent. So here, since we have 3 power functions being added together, here we're adding, this second term is adding a negative 7x to the second power. The degree of this thing is going to be 4. The degree of this polynomial down here is 5 because that's the largest exponent, and the degree on the bottom one is 3 because that again is the largest exponent. So because these polynomial functions, like I said, are a bunch of power functions being added together, we can determine the end behavior of a polynomial by looking at the degree of the polynomial, again the highest exponent, and the coefficient of that leading term. The polynomial is going to have the behavior, the end behaviors of these polynomials is going to behave exactly like that power function. So, for example, if this is my polynomial, just a generic, again, standard way of writing a polynomial, I can determine, again, whether this polynomial is going to behave like this power function, where the two ends are going to be pointing upwards, where the end behavior is behaving like this, by looking again at this first term here. If this term, again, in the very front, n, is equal to an even exponent, and a sub n, this leading coefficient here, this number right there, is a positive number, regardless of what all these other numbers that we're adding, regardless of what all these other power functions that we're adding to this first one right here, to the one with the highest exponent, this polynomial function is going to behave exactly like this power function, where the left end of the function is going to point upwards and the right end of the function is also going to point upwards. So this is going to be true again for all polynomials. Like if we, again, like on this polynomial right here, in order for this polynomial here to behave like this power function here, to behave like this power function where the two ends are pointing downwards, then that means that this number, or this, let's start with the exponent, this exponent of n has to be, again, an even number, and the number that we're multiplying this term with has to be a negative value. Regardless of what all these other terms are, simply looking at the term with the highest exponent, the degree, again, and the number in front of that term, that coefficient of that term, we can again determine how this polynomial is going to behave by those two values. So anything, again, any polynomial where the largest exponent is an even number and its coefficient is negative is going to behave like this power function, where the left end is going to be approaching negative infinity, and on the right end it's also pointing downwards. The function values are also, again, decreasing without bound. And the same thing is true here. In order for a power function to behave, a polynomial, in order for a polynomial to behave like this power function, where the left is decreasing without bound and the right is increasing without bound, that means that this exponent has to be an odd number and our coefficient has to be a positive number, because again, this thing is increasing, this thing is going upwards, it's increasing, so it has to have a positive value. And in order to flip it down and have it decrease, this leading coefficient, this number that we're going to multiply by, has to be negative, And the exponent there, again, also has to be odd. So let's look at some actual examples with some real numbers here, okay? So for example, number 1, right here. The end behaviors, to determine the end behaviors of this polynomial, we're going to look again at the term with the highest degree, which is this one right here at the very front. 4 is the highest exponent, so we're going to look at this there. Since the exponent on this value is 4, since the exponent here is 4, an even number, that means it's going to behave again like the power functions of even, so it's going to make a u. And the left end and the right end are going to either be pointing up or they're going to be pointing down. Since the number that we're multiplying, the x to the 4th power, is negative, that means that the two ends are going to be pointing downwards. So the end behaviors to this function is the following: that as x again decreases without bound, the function values are decreasing as well. And as x increases without bound, the function values are decreasing. So the two ends again are pointing downwards because of the negative and the even exponent. So we describe the end behavior using arrow notation as this. Let's look at our second example. In our second example, notice that the highest exponent here is 3. So the way that this polynomial function is going to behave, the end behaviors of this polynomial function behaves, are similar to the power function of all odd powers. So that would be either an increasing power function or a decreasing power function. And in this situation, because we're multiplying by a negative value, that's going to be this one right here, a decreasing power function. So to describe the left end, using arrow notation, we say that as x approaches negative infinity, the function values increase without bound. So we say the function approaches positive infinity. And the way to describe the right end, as x increases without bound, so as x approaches positive infinity, the function decreases without bound. So using arrow notation, we say that f of x approaches negative infinity. So this is the end behaviors to this function here. Now for number 3. Well, in this example here, notice that the largest exponent is 5. So the behavior, the end behaviors of this polynomial is going to be similar to the power function that increases or the power function again that decreases. And in this situation, because we're multiplying x to the 5th power with a positive 4, then that's going to be represented like this. The behavior of this polynomial is going to be the same as this power function here. So the left end, let's start with the left end. The left end, again, is pointing downwards. So that means that as x decreases without bound, which is written as x approaching negative infinity, the function values decrease without bound. So with arrow notation, we say that f of x approaches negative infinity. And on the right end, as x approaches positive infinity, the function values approach positive infinity as well. So this is how we describe the end behavior to this polynomial function here, by using again simply the leading coefficient test. Now normally your polynomials again have to be written in standard form, where the highest exponent is obviously always going to be in the front. But if for some reason your polynomial is not written in the standard form, again, you're not looking at just at the first term, you're looking at the term with the highest exponent. Because like I said, normally this is the standard way of writing your polynomial. Notice that the largest exponent is in the front, the second largest is next, and then it just decreases by terms. And the term at the very end should always be your constant, the one that doesn't have an x. Now let's look at the last example. So for this example right here, this polynomial function is going to behave like this power function here, like 7x to the 6th power. Now all of these other terms are simply going to make the polynomial again curve in between. But overall, the behavior of this function is that the left end and the right end are going to be pointing upwards. And of course, all these other terms just simply make the curve, the polynomial curve up and down, intersecting the x-axis at various places, okay? But what we're focusing on, okay, is the left and right end. Where are they going to be pointing at? So in this example here, since we have an even exponent and a positive coefficient, that's going to behave like the power function pointing upwards, like the one that makes a U, again, pointing upwards. So the left end is described by using this arrow notation. So as x decreases without bound, f increases without bound. And as x increases without bound, f of x increases without bound. So this is how we describe, again, the end behaviors of our function. Now, in order to determine, again, more information and working backwards, we can also determine, again, those two numbers, determine what type of numbers we're going to have, again, at the front, at the leading coefficient, and the degree of this exponent, of this polynomial. We do that by simply understanding, again, the turning points and how many times the polynomial turns. Since a polynomial is a smooth curve that's continuous, the degree of the polynomial is greater than or equal to the number of turning points plus 1. Now remember that a turning point is simply defined, it's going to be defined where the function increases or decreases, and it changes again that direction. So the point in which the polynomial switches directions is the number of turning points. And the relationship between the turning points and degree, like I stated earlier, is that the degree is greater than or equal to the number of times it turns plus 1. So for example, let's say we have this polynomial here, okay? I know it's a polynomial because, again, it's continuous, it's connected through every single value of x, and the turns are smooth. They're not, again, like a sharp corner where it changes direction like a letter V. So I know that this is a polynomial. And because I know that this is a polynomial, I know that I have a bunch of power functions being added together. Now, because of the way that the two ends are behaving, because the two ends are pointing downwards, I know two things. I know, first of all, that this letter A is equal to a negative number. And I know also that the exponent of n is equal to an even value. Now, I know even more information about the value of n. Because of the number of times it turns, we have 1, 2, 3, 4, 5. I know that this exponent, the highest exponent, is going to be an even value that is greater than or equal to 5 plus 1. 1, 2, 3, 4, 5, and add 1 is going to be 6. So I know that this exponent, the largest exponent, again, the degree of the polynomial, is going to be a number 6 or greater, an even number specifically, an even number greater than or equal to 6. And because the two ends are pointing downwards, I know we're multiplying this function with a negative value of a. What those numbers exactly are, we're not going to find today, and we're not going to be looking into that. All we're going to use, again, is using this idea of the leading coefficient test in order to determine, again, the type of numbers that these functions have. So for example, number 6, again, because this is a polynomial, and again, because it's smooth, it changes direction in a smooth curve, and everything is connected, I know again that this is a polynomial. So I know that it's written in this format. As a result, a bunch of power functions added together. And because it's a polynomial, I know that this exponent is going to be an exponent that's going to be greater than or equal to 1, a whole number greater than or equal to 1. And a is going to be any real number. Positive, negative, fraction, decimal, doesn't matter. But I know it's going to be, again, any real number. So let's see what information we can get. Well, because this is decreasing, we have one end up and one end down. This graph is decreasing. So we know that the value of a is going to equal to a negative number. Now, what about the exponent? Well, since the two ends are pointing in opposite directions, that means that our exponent is going to be an odd number. That is greater than or equal to 1 unit higher than the number of turning points. So let's count the times that this function changes direction. So we have 1, 2, 3, 4 turning points, and 4 plus 1 is 5. So it has to be an odd value. The exponent is going to be an odd number that is greater than or equal to 5. Let's see, let's do 2 more examples. Let's see, try this example next. Pause the video and determine again the number, determine again the degree and the leading coefficient. So let's check your work. So since f of x again is a polynomial function, we know that we have something that looks like this. And a is going to be a negative number because the two ends are pointing again in opposite direction. This graph is decreasing. Of course, it goes up a little bit, but then eventually it goes down again. So this is decreasing. So that means that the value of a is negative. And the exponent is going to be an odd number again because the two ends are pointing in opposite directions. That is greater than or equal to 3. And I know it's 3 because since it turns 2 times, it has 2 turning points. 2 plus 1 is 3. So that's what this exponent up here has to be. It has to be 3, 5, 7, and this leading term right there has to be a negative number. Let's see, try the last one again by yourself. So pause the video, determine again all the same information, and come back and check your work. So let's check your work here. So our polynomial function a times x to the power of n plus a bunch of other power terms. The leading term is going to have a positive number, and the degree is going to be an even value that is greater than or equal to 4. And 4 because there's 1, 2, 3 turning points. 3 plus 1 is 4. So this is again what the leading term to this polynomial equals to. Okay, so we have information about the leading term. Well, that concludes again the examples on this lesson 2.3 polynomial functions. Again, if you have any questions, please send me a message on Remind or through email. And I again appreciate you watching, and I hope you have a wonderful day.